So in this chapter, or parts of chapters, we're going to talk about equations and reactions, how to balance them. We're also going to talk about different types of reactions and ways to classify them. And then we'll talk about a few other things, I think. So we're going to start with really the chemical equation. And the chemical equation is really what we use to represent a chemical reaction happening. A chemical reaction is a chemical change. So what we start with and what we end with are fundamentally different things. And you cannot get them back by any type of physical means like boiling, freezing, filtering, those type of things. So when we look at an equation, there's different ways we could represent a chemical equation, but most of the time we represent the chemical equation obviously with the formulas of whatever is reacting and whatever is being formed as a result of it. And when we look at an equation, it is always reactants on the left-hand side of the arrow going to products, with obviously our reactants being our starting material. And obviously our products is what is formed as a result of that chemical reaction. Other things that we see in a chemical equation is very commonly we do see the different states of everybody that's in there. So S is solid, L is liquid, G is gas, and probably the one we see a lot is AQ, which is aqueous. That is a water environment. That is really a solution. And there is a difference between L and AQ. And just to illustrate the difference between it, if you had something like water, that would be a pure liquid by itself. Now, if you took something like water and you took some sodium chloride solid and dissolved the sodium chloride solid in the water, that would make a sodium chloride solution, and that would be an aqueous guy. So if it's an L, it's a pure substance by itself, really nothing else in there. If it's aqueous, it is basically a solution, which is a homogeneous mixture of two things or more. And they are both obviously in the liquid state, but there is again a difference between sort of aqueous and a liquid. Other things that we obviously will see sometimes in reactions as well is up on the arrow here. Up on the arrow, we'll sometimes see things written. So a couple of things that we may see there written on the arrow. We may see a delta symbol, and that delta symbol on top of the arrow usually means heat. We also will sometimes see up on top of the arrow a catalyst or catalyst, and catalysts are, they are not reactants. They are not products either. And they actually do not get used up in the reaction. For the most part, the catalysts are there to speed up a chemical reaction. There are catalysts that actually will slow it down, but most of the time, if somebody is talking about a catalyst, they're probably talking about it in the effort of speeding up a chemical reaction. And that's a lot of times what you will see kind of written on the arrow. It may be a metal, for example, that does that. It could be like an acid, so H plus may be written on top of the arrow. How a catalyst works, we'll get into sort of in the very last chapter, but essentially, catalyst is able to sort of find a more efficient pathway for that reaction to occur. And because it's more efficient, it will pretty much occur a little bit faster. So for example, that could be something as simple as a piece of metal or something that we have, say, gas molecules flying around. They may be attracted towards that metal, and that's going to bring everybody in contact with each other a lot quicker than if that catalyst wasn't there and they're just flying around trying to find each other. So it kind of almost brings like a central location for everybody to come, and that's going to allow a lot more reactants to react and make products. Now, when we have a chemical equation, obviously it should always be balanced, and that's a really important part. And as we'll talk about after this, we could also use a chemical equation to do calculations to figure out things like how much product you should produce if you did a reaction, or if you knew how much product you produced, you could figure out how much reactants you started with. Stoichiometry basically is what that is. When we look at this, we can read this equation a couple different ways. Just looking at the coefficients here, we could say that there are two atoms of magnesium react with one molecule of O2 to form two formula units of magnesium oxide. Formula units are sometimes used for ionic compounds instead of molecules because, again, they're not sharing electrons and stuff like that. So sometimes people will use formula units when it's an ionic sort of compound involved. The relationship that we use probably the most and will use with stoichiometry is really what is sometimes referred to as the mole to mole relationship. And again, it is just the coefficients. So we could say for every 2 moles of magnesium, react with 1 mole of oxygen to produce us 2 moles of magnesium oxide. The last one here is the conservation of mass. So if we add up the molar mass of all of our reactants, they should equal the molar mass of all of our products, even though those things may be in different sort of compounds and molecules. They are still the same molar mass on each side of the equation. So we really start with about 80 grams of reactants, and we would end in this case with about 80 grams of products. With that being said, again, the only relationship that we don't use from those coefficients is a gram to gram relationship. So we don't do that type of relationship from those coefficients. An equation should always be balanced, and no matter what you're doing, if you have an equation, that should really be the first thing that you check. And that's the idea. In a chemical reaction, the only thing that happens is we break bonds. So that's just electrons. So the only thing we do is break bonds. We don't do anything with the protons or neutrons in the chemical reaction, which means we don't touch the nucleus. And because we don't touch protons, we never change elements either. So we have conservation of elements as we go from one side to the next because of that. And we should always have the same number of elements on each side of the arrow. Once again, that is just something you should always look at when you have an equation. If you do not see coefficients, you should definitely take a pretty hard look at it and make sure it's balanced. And if not, you should balance it. If you do see coefficients, it never hurts to take a quick look just to make sure. But usually I would say if you see coefficients, you're probably relatively safe that it's going to be balanced. So let's talk about a few of the ways that you could balance equations. One of the most important things is you want to always start with the correct formulas. So if you're given everything in words, you definitely want to make sure that you put down on your paper all the correct formulas first, just like you were doing nomenclature, regardless of the balancing part. And that is something that people kind of mess up on. They start with the wrong formulas and they sit there all day trying to balance something that will never balance because you don't have the right formula. So that's a very common sort of error. It should always be in this order. You should always correct formulas first and then balance. You should never try to do it together, which oftentimes happens, for example, when you have the front part of the equation and you need to predict what comes on the back part of the arrow. So very commonly when people try to put things together for the back side here, they end up trying to balance and write the formula at the same time. And again, never do that. Always start with correct formulas, regardless of the balancing, and then you go back and balance. So here we have ethane reacts with oxygen to form carbon dioxide and water. And here we would want to get our correct formulas down first. So this is ethane. Oxygen, remember, is a diatomic molecule. So again, a common mistake that people make is they just write O for that, or H for hydrogen, or N for nitrogen. So remember, those guys come as twos. They are also sometimes referred to various ways in words. They may say oxygen gas. They may say just like this, oxygen. They may say molecular oxygen. So sometimes those kind of diatomic molecules, which are elements, are referred to in a few different ways. Obviously, carbon dioxide is CO2 and water there is H2O. So what we want to do is we want to take our equation here, C2H6 plus O2 gives us CO2 and water. And once we have all of the sort of correct formulas down, this is what is known sometimes as the unbalanced equation. And pretty much in chemistry, an unbalanced equation is useless because you can't really use it correctly for anything. So the idea here is we do want to balance it, and a couple of main rules is we only change the coefficients. So we only balance by changing the coefficients. Those are the numbers that come in front. Why, for example, do I not change the subscripts? Then I change pretty much what it is, right? So it'll no longer be what it was. We also don't do any weird things like put big numbers in between elements or anything like that. So we don't do anything weird like lay a 3 or something like that in between something. I know it seems logical, but I've seen it done, so don't do that. Now, we obviously want to continue to use coefficients until we have it balanced. And when you have a properly balanced equation, there's really two things that you need to make sure of. You need to make sure that all of the coefficients are whole numbers, and they need to be the simplest set of whole numbers. So what do I mean by the simplest set of whole numbers? Let's just say that you balance this equation here and come back here and do it. You had a 2a, a 4b, and a 6c. And we'll just say this is a balanced equation with those coefficients. When I look at those coefficients, I could do what with them? I could divide them all by 2, right? And you should do that to give you the properly balanced equation that looks like this. So sometimes that does happen because people could see maybe larger numbers to use as coefficients, and it could still obviously be balanced. But if you can go through all the coefficients after you're done balancing your equation and reduce them down to the smallest set of whole numbers, again, they still need to be whole numbers. You should do that to have the properly balanced equation. Any questions on that there? All right. So how should you approach this? I personally am a fan of like making a little table. It kind of helps direct you maybe where to go, what you might want to start with. So there's the reactant side, there's the product side. We got some carbon, hydrogen, oxygen happening. On the left-hand side, I got 2 carbons. Right-hand side, I got 1. Left-hand side, I got 6 hydrogens. Right-hand side, I got 2. And left-hand side, I have 2 oxygens. On the right-hand side, I have 2 oxygens there, plus 1 more there, which gives me 3. So making a table sometimes will help you maybe focus in on what is maybe the easiest thing to fix. And I personally would start with what is probably the easiest to fix. And that's usually something that's probably only in one thing on each side. That's kind of a good thing to start with. So for example, if we look at the carbon here, I have 2 on the left and I have 1 on the right. I can easily fix that by putting a coefficient of 2 in front of the carbon on the right. That is then going to go for everybody behind it. So it does count for everybody behind it, and we have to multiply. So we got 2 carbons. We still have 2 hydrogens. Now in terms of oxygen, we have 4 here in the first one, 2 times 2, and we still got the 1 over here. So now we are up to 5 in terms of our oxygen. Now, what should I do next? I fix the carbon and everything else is still not balanced. So the next place that I want to go to, I have an option really here of hydrogen or oxygen. I am going to save the oxygen for the end. And the reason I'm going to save the oxygen for the end, when I look at oxygen in this equation, I have oxygen in one thing over here, but oxygen seems to be in a couple of things on this side. But when I look at hydrogen, I got hydrogen in one thing on the left and only on one thing on the right. So that's going to be much easier to fix and save sort of that oxygen that's in multiple things for the end. So that is where I'm going to go next, which is hydrogen. So I got 6 on the left, 2 on the right. That means I do need to put a 3 in front of the water, which once again will go for everybody behind it. That's going to give me still 2 carbons. 3 times 2 is 6 hydrogens. Now in terms of oxygen, I still have 4 on the first one, but now I have 3 more here on the last guy, which gives me 7 at this point. Any questions on that so far? So now we got carbon balance, we got hydrogen balance. The only thing that's left now is oxygen, which we saved for the end because, well, it was going to be a pain. So clearly we don't want to change any of the numbers on the right-hand side because they're kind of locked in a little bit. So we've got to do something over here to turn it into a 7. So we got 2 on the left, we have 7 oxygen on the right, and we need to turn it into a 7. So one way that we could do that is we could actually use a fraction to do that. We could go 7 over 2, for example. And if I do that, I now have 2 carbons, 6 hydrogens. And when I take 7 over 2 times 2, they cancel and leaves me 7. That equation now is balanced, but is it properly balanced? It is not because we have a fraction, which we cannot leave. So we can definitely use the fraction to balance the equation, and you sometimes need to do that. And this is a very common situation where that occurs, where you have like a diatomic molecule on one side and that element and a couple of things on the other side. We need to clear the fraction. So to clear the fraction, we need to multiply the entire equation here by the denominator, which is a 2. And if I do that, that will give me 2C2H6 plus 7O2 will give me 4CO2 and 6H2O. And if I didn't screw up anything here, we should still be balanced. So I got 4 carbons on the left, 4 on the right, so that's good. I got 2 times 6 is 12 hydrogen on the left. 6 times 2 is 12 on the right, so that is good. 7 times 2 is 14 oxygens on the left. In this first guy, I got 8 oxygens. In the second guy, I have 6. So that also is 14. And now we are correctly balanced in terms of this equation. Do you have to use a fraction all the time? You do not, but this again is a common situation. Now you may ask yourself, how do I know what fraction to use? It's pretty simple. The number that goes on top is the number you need. So if you remember on top here, we needed to turn this into a 7, which is what we did. The number on the bottom should always match the subscript. So this number down here should always match that number so they cancel out as well. And you'll always have the right fraction that you need to choose. Any questions on that? So if you make a little table, kind of help you. You don't necessarily have to make a table, but at the end, you might want to just double check that it is balanced. Any questions on that there? All right, so let's take a look at a few more here and let you practice a few. And I'll scroll this by. It's pretty much what we just did, in case you want to see it. Okay, so let's take a look again. If we kind of table it up here, I got 1 nitrogen on the left. I got 2 on the right. Oxygen on the left, I got 1. And on the right, looks like I got 1. And lastly, hydrogen on the left, I got 2. And on the right, I also have 2. So clearly here from our table, we can see everything's balanced except for the nitrogen. So it seems like a good place to start. We're going to put a 2 in front of our nitrogen on the left. That again goes for everybody behind it. So that's going to give me 2 nitrogens. We now will have 2 oxygens and we still have 2 hydrogens. And very common when you're balancing equations, you fix one thing, kind of screw up something else. So that's very common. We can still see from our table that perhaps now oxygen would be a good place to go to, as that's the only thing that's not balanced. So we would need to go to the right-hand side here and put a 2 in front of the oxygen, which also goes obviously for the hydrogen that's there as well. So that's going to be a 2. We have 2 oxygens, and now 2 times 2 is 4 hydrogens. So we're getting close. We got these guys locked down and balanced. Now we could fix the hydrogen very easily by going back to the left-hand side and multiply or putting a coefficient there, which will give us 4, 2, and 2. And now we are balanced here. Any questions on that one there? All right, let's take a look at a few more here. All right, balance this equation, see what you get. Okay, so let's take a look again. We're going to make a little table here. We got 3 carbons on the left, we got 1 on the right. We got 8 hydrogens on the left, 2 on the right, 2 oxygens on the left. Again, we do have 3 oxygens total, 2 in the first one, and 1 more there in the water, which gives us 3. Again, not much here that is balanced. I'm going to start with what seems pretty easy to balance, which would be the carbon, perhaps. So if I start with the carbon there, I'm going to put a 3 probably instead of a 2 would be better. There we go. A 3. And that's going to give me 3 carbons. We will still have 2 hydrogens. And at this point, we now have 3 times 2, which is 6. And we still got 1 more over there, which gives us 7 oxygens at this point. Once again, here I'm going to save oxygen for the end, as it's in multiple things on one side and by itself on the other side. Hydrogen is just in one thing on each side, which makes it much easier to work with next. And we can fix the hydrogen by putting a 4 there in front of the water. That's going to give me 3 for the carbon. That's going to give me 4 times 2, which is 8 for the hydrogen. And remember that that also goes to the guy in the back there. So we got 6 oxygen in the first one. We now will have 4 in the second one. And that's going to give us a grand total of 10 here. Now, as you can see, saving that oxygen for the end made it a lot easier, because now all I have to do is put a 5 there. And now I have 3, 8, and obviously 5 times 2 would be 10 in this case. Any questions on that there? For the oxygen? Yeah, so we have a 3 in front here on the CO2. So basically be 3 times 2 here, which would be 6. And then we have a 4 over here in front on the water, which would go to the 1 oxygen back here. So 4 times 1 would get you 4. And then if you add those together, that is where the 10 comes from. Yeah. Other questions? Yeah, so again, the coefficient in front goes to everybody behind it. So you do have to kind of distribute it to everybody that's behind it. Any other questions on that? Try a few more here, just make sure. Write the balance equation, a little boron, I'll spit it out there, maybe. Diboron trioxide reacts with water to form boric acid. So diboron trioxide, that is a type 3, some prefixes, so that should be a B2O3 plus water, which we should know, right, is H2O, forms our boric acid. So that would be our unbalanced equation there. So balance that one up, see what you get. Okay, so let's take a look at this one. Same approach here. We got 2 borons on the left. We got 1 on the right. On the left-hand side, we have 3 oxygens here, and we don't want to forget the 4th one that's right there. So we got 4 oxygens, and we have 2 hydrogens. On the right-hand side, we have this guy that does get multiplied into everybody in the parentheses, so you have to distribute them in. So that would give us 3 oxygens and also 3 hydrogens in this case. So if you have something with parentheses and a subscript, you do have to kind of multiply that into everybody inside the parentheses and counts for them. Once again here, there's not much to work with, so I'm just going to start with the boron and fix that. And I can fix that by putting a 2 in front. When I do that, that gives me 2 borons. Now, in terms of the oxygen, I do need to multiply this 3 in, which would give me 3. but I also need to multiply it by the coefficient on the outside as well. So that's basically 3 times 2 is 6 of those. Same thing for the hydrogen, 3 times 1 is 3, and then I got to multiply it over here to the 2 as well, which would give me 6. So again, the coefficient goes for everybody behind there, even if they're in parentheses, and you still need to obviously distribute what's in there. Any questions on that there? And again, what that basically means when you see the OH with the 3 is you got 3 of these, right? And now that you have 2, you basically have another set of them, right? And that's how we get to basically 6 of each of those total. At this point, we clearly don't want to do anything with the guy on the right-hand side because frankly, that's just going to be a long day if we do. So we have hydrogen and oxygen here, and you can probably guess which one I'm going to go first at. I'm going to go first at hydrogen, as oxygen again is in multiple things. I'm going to save that for the end. So I'm going to try to fix the hydrogen here, and to fix the hydrogen, I'm going to put a 3 in front of it to get me to 6. That gives me 2 borons. In terms of the oxygen, I have 3 here. This 3 goes to both, which means I actually have 3 more oxygens there, which is 6. And 3 times 2 is 6. So in this case, by fixing the hydrogen, it also fixed the oxygen, which sometimes happens when you're balancing equations. Sometimes you put a coefficient to fix one thing and actually will fix multiple things along the way. Any questions on that there? Okay. All right, let's try another one here then. All right, balance this equation up, see what you come up with. A little ammonia, a little oxygen. Okay, so let's take a look and see. We got 1 nitrogen on the left there and 1 on the right. Hydrogens, we got 3 on the left and 2 on the right. And oxygen, 2 on the left, and we do have 2 on the right there. So everything is balanced except for the hydrogen. In this case, we actually probably need to put a number on both sides here. And 3 times 2 is 6. So we probably want to get them both to 6. So to get my hydrogen on the right-hand side to 6, I need to lay up a 3. Get my hydrogen on the left-hand side to 6, a 2. That is now going to give me 2 nitrogens. 3 times 2 is 6 hydrogens, and still 2 oxygens. On the right-hand side, we have 1 nitrogen still, and 3 times 2 is 6 for the hydrogens. We still have 1 oxygen there. We now will have 3 more oxygens here as that coefficient goes again for both things behind it. And that will then get me, looks like 7, if I'm counting that right. At this point here, no, that's a very bad count. How about a 4? There we go. So 4 oxygens here on the right-hand side. Now we fixed the hydrogen. We clearly messed up everything else. Again, I'm going to roll in this case with the nitrogen, as the oxygen's in a lot of things going on. I'm going to save that for the end. So I could easily fix the nitrogen here by putting a 2, and that will give me 2 nitrogens. In terms of hydrogen, I still have 6. Now oxygen, I'm going to try to do a little better here. 2 there, and we still have 3 here. So that gives us 5. Again, at this point, there's only 1 spot left to go, which is here, which we save for the end. And this is definitely a situation where you got to turn that 2 into a 5. So this is a fraction situation. And again, how you choose the correct fraction is the number we need, which is 5, goes up on top. The number here should go on the bottom and match. And now we will have it properly balanced. So we have 2, 6, and 5/2 times 2 is 5. Once again, although we can use a fraction here, we do need to clear the fraction by multiplying everything by the denominator, which is multiply everybody by 2 in this case. And that will give us, looks like 4NH3 plus 5O2 gives me 4NO and 6H2O. And once again here, if we didn't mess anything up, we should still be balanced. Got 4 nitrogens on the left and 4 on the right. I got 4 times 3, which is 12 hydrogens on the left. 6 times 2 is 12 on the right. I have 5 times 2 is 10 oxygens. And here we have 4 oxygens. And in here we have 6 oxygens, which is 10. So we are balanced in this case. Any questions on that one there? All right, so a couple last ones here. Balance these guys up, see what you come up with. Sometimes it's easier because what we do see in these equations are our favorite things, which are polyatomic ions. And we do see polyatomic ions on each side of this equation here. And we actually see in this first one a couple of different polyatomic ions, but they are basically on opposite sides in the same form. So when you go to balance an equation that has polyatomic ions in it, sometimes it's easier to not go element by element, but kind of keep the polyatomic ions together and just balance them as whole units rather than kind of going element by element. So in this case, when I look on the left-hand side and the right-hand side, I got one carbonate basically on each side. So I'm not going to start there. But on the left-hand side, I have 2 phosphates. And on the right-hand side, I have just 1 phosphate unit. So that is where I'm going to start to balance this. I'm going to put a 2 here, and that will give me 2 phosphates. Now, when you do this method of kind of keeping the polyatomic ions together to balance the equations, as soon as you put that first coefficient in and it balances that polyatomic ion, whatever it's attached to, which in this case is my sodium, that is where you should go next. So 2 times 3 for the sodium is 6. So that is where I should go next to balance it. To balance my sodium on the left-hand side to make it a 6, that would be a 3. Now I should go to whatever's attached to my sodium here, and that is 3 carbonates, which then brings me back to the right-hand side where I need to put a 3 for my carbonate and also gives me 3 for my iron, which is great because that is what I need. So it's oftentimes a lot faster to balance equations that have polyatomic ions in it if you kind of keep them together rather than go element by element. You can still go element by element, but there's a lot more kind of multiplying in and multiplying out of parentheses a lot of times, and probably a greater chance maybe of error happening if you kind of take that approach. Any questions on that there? So now if we come down here on the bottom one, we also have some polyatomic ions happening. We have sulfate here on the left. We have sulfate on the right. We also have hydroxide here on the left. And we have hydroxide on the right. Now, in this case, we actually have different amounts, if you will, of each of these polyatomic ions. So you can choose either one to start with. And in some cases, one might work better than the other. And for example, if I started with hydroxide here, I have 3 hydroxides on the left, 1 on the right. I'm going to put my 3 here, which will give me 3 hydroxides. That gives me 3 silvers. But when I come over here, I have 2 silvers, so that's not so great. And we can then erase it and start again with the other polyatomic ion, but I'm just going to rewrite it for a reason. I'll show you in a second why. So I'll just erase it and we'll start with the other polyatomic ion, which will be our sulfate in this case. So I have 3 sulfates on the right, 1 on the left. So I'm going to put a 3 there. That's going to give me my 3 sulfates. Again, I'm going to go to whatever it's attached to, which is now silver, and that is 6. And I'll put my 6 here for the silver. That then gives me 6 hydroxides. That is where I should go next. Put a 2, 6 hydroxides, 2 chromiums, and now I'm balanced. Question on that one. So what I was doing, going to do before it just reset there was if you screwed up a little bit and kind of chose maybe the wrong polyatomic ion to start with, it's not really all lost per se. So you could either do what we just did was kind of erase it and start again with the other polyatomic ion. Or if you did what we did originally, which was we put a 3 here for our hydroxide, and then that gave us 3 silvers, and obviously we see it's not so great. We can then take 3 times 2, which is 6. Just erase that and put a 6, and then we could just pick up at that point. That would give me 6 hydroxides and 6 silvers. Then I could put my 3 there for my silver. And that gives me my 3 sulfates. And that also gives me my 6 hydroxides I need. So you could kind of do that and pick up for the middle, or you could just start with the other polyatomic ion as well. Any questions on balancing equations? All right, we're laid up there.